group in Masa. His research interest covers many topics in computer graphics and computer vision, including appearance modeling and rendering, texture and synthesis, light transport analysis, and 3D deep learning, performance capture, and the facial animation, as well as graphics systems. Dr. Tong has published more than 120 papers in top computer graphics and vision journals and conferences, including 55 ACM SIGGRAPH and talk papers. He serves as associate editor of computer graphics journals such as ACM Talk, TVCG, and the CGF, and the paper committee member of ACM SIGGRAPH and SIGGRAPH Asia, Eurographics, and Pacific Graphics. He is also the associate editor of IEEE CGA, CVMG, and Visual Informatics. So Dr. Tong obtained his PhD degree in computer graphics from Tianjin University in 1999, and his bachelor degree in master degree in computer science from Zhejiang University in 1993 and 1996, respectively. So we are very glad to welcome Dr. Tong to give the first representation about the Man the Gap learning 3D representation from 2D image collections. So welcome, Dr. Tong.
Yeah, thanks, Professor Sun, for the kind of introduction. So I think everyone can hear me, right? You can hear me very clearly, right?
Right. I can.
Okay, let's start. Yeah. So it is my great pleasure and honor to be here to introduce our recent research works. So the topic of my presentation today is Man the Gap, learning the 3D representation from the 2D image collections. So in recent years, the deep learning has demonstrated its advantage in many fields, such as the image and video understanding, speech recognition, machine translation, as well as the 3D graphics, of course. So compared to the traditional methods, the neural networks provide compact nonlinear representations and unified network architectures and training schemes for different tasks, as shown here. So for 3D graphics, the deep learning enables new approaches and solutions for shape modeling and generation, realistic rendering, character animation, and physical simulation. Despite these progresses, so compared to the other fields such as computer vision and natural language processing, so if we look at the graphics field, the advances of the 3D deep learning is still relatively slow or behind. A key challenge of the 3D deep learning is the dimensional gap between the 3D representation and its observation. So on one side, the 3D graphics representations used to model the geometry, appearance, and the dynamics of the 3D world are always high dimensional, such as the 3D geometry, 6-dimensional surface reflectance data, or the 4D deformation sequences of the closed mesh or other human characters. So on the other side, the imaging devices are always 2D or even 1D, and the data we can directly acquire from the 3D world is the 2D projections of these high-dimensional functions. So this dimensional gap results in a set of blocking issues for 3D deep learning, such as diverse and irregular 3D representations, small 3D dataset available for the network training, and difficult data labeling. So a natural question is that, so whether we can bridge this gap. In other words, can we directly learn 3D representation from the 2D image collections? If we could do this, we can get lots of benefits from the huge amount of image video dataset in computer vision field and learn the high quality 3D representation from the realistic image captured from the real world. However, this is also a very challenging task. So obtaining the 3D representations from the 2D images is a well-known ill-posed inverse rendering problems. So researchers in the vision field or in the graphics field have worked in this area for more than 30 years and still cannot get a good solution. So our task is even more challenging than the 3D reconstruction or inverse rendering because the images in many cases are captured from different objects and we do not have multiple views of one object in the image collections. And also, in many cases, we do not have correspondence between these images, and also sometimes the lighting is unknown. So to tackle this challenge problem, researchers have developed a set of methods. We classify these approaches into the two groups. So the learning by reconstruction or synthesis, or learning by discrimination. The first set of methods try to learn 3D representation by reconstruction. So the general idea is to regress 3D representation from 2D images so that the rendered images of the learned 3D representation match the input real images. The key technical challenge of these methods is to solve the ill-posed inverse rendering problem with the limited amount of the labeled data. In particular, the images and their underlying ground truth 3D data always is not available, especially the underlying ground truth 3D data. Yeah. So the second set of methods, I named them as a learning by discrimination. So these methods try to learn the 3D representations from the 2D image collections by discrimination. So the basic idea here is to learn a 3D generative model from the 2D image set. So if the images rendered by the generated 3D representations cannot be distinguished from the real images, then we assume or we regard the learned 3D representation is the correct one. So the key challenge of this method is to minimize the quality gap between the synthesized image and the real ones and preserve the 3D consistency of the learned GAN models. Note that this task somehow is different from the traditional GAN for the 2D image generation, just because in the traditional GAN, always we try to train a GAN only for 2D image generation, and the data set is only also the 2D image. And although it can generate a high quality result, however, this GAN method cannot make sure the generated image will preserve the 3D consistency, which means when you rotate the head and try to get the head from other viewpoint, it will be a different head. You cannot get the exactly same head or same face. Yeah. So in the past several years, our group has done some explorations along these directions. So in the following part of this talk, I will introduce two works we have done in these two categories and describe how we solve the key technical challenges in each work. So the first work is the self-augmented Svprd modeling. Its method try to learning from by reconstruction. So the goal of this work is to develop a convolutional neural network that can automatically generate the material maps from a single texture photograph downloaded from the internet or captured from the real world and avoid the tedious manual work always done by the artist. So specifically, given a photo of the flat real material surface as shown below, and we want to generate the diffuse color map, bump, normal map, or the geometry details, and the specular parameters for the whole map so that the material can be mapped on other 3D surfaces or shapes and can be rendered under the no lightings. So the work was done by the Xiaoli, Yue Dong, Peter Pierce, and me, and has been published in the SIGGRAPH 2017. So the key challenge here is still solve the ill-posed problems there. And there are three challenges. First, as we discussed before, is that always for the material maps, if you want to get it, we don't have sufficient number of the ground truth material maps and the images there. That's very clear, just because if we already have many ground truth material maps, we needn't to do this task, right? So always the real case is that we don't have so many or large amount of ground truth material maps and they are rendered images for us to do the training. And the second thing is that when we want to try to derive the material maps from one input image, it's always a ill-posed problem, which means one input can result in different materials, maps, results there, all can be rendered to the same input image. So we need some priors of the Svprdfs or lightings to do that. However, different from other cases such as the 3D face or bodies. We don't have the generic prior model of the Svprdfs or the surface reflectance layer. And the last thing is that given this input image, we don't have any knowledge about the lighting of the input image, which means we cannot use people all call the self-supervised learning approach to do that, which means people only scout the input image. And when you got, if you know the lighting, when you got the result surface material maps, you just render the surface material maps to one image with the known lighting. Then you make sure the rendered image should be same as the input image. But here, the lighting is unknown, so we cannot do this self-supervised way. Yeah. So to tackle these challenges, so we have some key observations. So our key observation is that although the labeled data, which means the image and their ground truth material maps, are difficult to collect, fortunately, it's easy to obtain a lot of unlabeled images. Such image could be collected either from internet search or from some previously released dataset, for example, the Cornell open surface dataset. Moreover, for this single image material modeling problem we want to solve, we actually have a well-defined or well-known, well-developed inverse mapping, which means the rendering. So our task, note that our task is getting the appearance of surface reflectance map from one single image. But if we're given the material maps, we can render out a very realistic image, which is our input by the rendering. Yeah. So based on these two observations, we have several key ideas. The first one is that to solve the data problem, we want to use a small set of images with the ground truth material maps and a large amount of unlabeled image for this training task. And then the second thing is that for the general prior models of Svprdfs, we don't have this. So we want to use the CNN models, the neural networks, during the training as a prior of the Svprdfs for this precise. And finally, although the lighting of each unlabeled image is unknown, and we cannot use a self-supervised way for the learning, now, so we suggest we try to use the unlabeled or the real input image for data generation, which means we want to use it to generate some material maps, but not for the loss functions. And based on these key three ideas and our key observations, we design a self-augmented CNN training scheme that uses both the labeled data and the large amount of unlabeled input to train our network with the help of the rendering precise. So here is the details, let's say. So in particular, we first start from the supervised training with a few labeled data, which means the input image and their ground truth surface material maps. So of course, few labeled data is not enough for training this task. So our several epochs, our several iterations, we obtain the initial CNN models. Given one labeled input image without ground truth appearance, we feed it into the network and got the predictions. Note that this prediction, although it is a material map, is not the ground truth material of the input image because the network still have errors, right? The network is still bad. However, remember that our key observation is that we have the render as a known inverse mapping. So given this predict material surface maps, we could render a new input image using the predicted material data under some synthetic lighting or the real environment lighting we captured from the real world, which is much easier to obtain it. So since the render is a ground truth precise, we actually got a new pair of the training data with the rendered image as the input and predict the appearance as the ground truth. So we use these pairs generated by current convolutional neural networks as the labeled training data for the training and update the CNN models. And we repeat these three steps until the CNN training is converged. This is the pipeline of our self-augmented training. We call it the self-augmented training since the data is generated with the network itself on the fly during the training process. So here we compare the result generated by the CNN training with our self-augmentation scheme and the CNN trained without self-augmentation. So for the input image on the left, the first column shows the result diffuse map, and the last column is the image of the material rendered under new lighting conditions. The third row is the ground truth, and the first row is our result generated by our self-augmented training, and the second row is without self-augmentations. So you can see that our self-augmented scheme using the information in the unlabeled data and get better CNN models. Without self-augmentation, the prediction will have artifacts such as the burn spot in the diffuse textures and show in the box, and a significant large specular layer. So here we show more results generated by our scheme, such as wood, metal, and plastic. Yeah. So here we show some follow-up works. So after we got this work, we also published another paper to discuss. So in this work, we still need some ground truth material maps, capture material maps, and real images. So the question is that, do we really need this realistic material maps captured from real world? So our following up work shows that actually it's not. So we can use some synthetic rules to generate some synthetic material maps and for this training, so totally avoid the real captured material maps for this training process. And later, and based on the idea, we also developed a more general deep learning based approach for Svprd estimation and published in SIGGRAPH 2019. Yeah. So we just introduced how we use the learning by reconstruction framework to do the Svprd modeling. Now, the second work I want to introduce is a learning by discrimination method named the generative radiance manifold of Graham for 3D aware image generation. So the goal of this project is to generate in 3D neural radiance field, or we call the nerves of the object in a class from their 2D image collections. So as shown here, the input is a collection of the 2D images. Each one might be captured from the different object instance, or such as in the face case, it's a different identity. The output of our method is a GAN model or the generative models that can generate nerves for rendering high quality 3D consistent images from different viewpoints, as shown on the right. You can see that for these people, for each identity, if we render it from different viewpoint, this image are really consistent and realistic, just like it's rendered from the true ground truth 3D real models. So before we go into the details of our method, let's first check the related works and figure out the key challenges in this task. So the core representation of our method is the neural radiance field, or called the nerve, which models a 3D object with a 5-dimensional radiance volume of the density and the view-dependent color defined at each point in the 3D space. So given a nerve, we can generate the image for a specific view via traditional volume rendering by integrating the transmit and color along each ray, and by sample this volume with a settle point. So the original nerve proposed and published in the ECCV, and it's a great paper. And the original nerve is reconstructed from the multiple view image for one object. So it's the original nerve is designed for reconstruction task. So here we want to apply this representation for generation tasks, which means we want to use it as output of a generative models and use for generation. So for this one, we need to solve the two problems. So first, the computation and memory cost of the nerve for GAN training is extremely large. So as shown here, to train a GAN for generate a nerve that can render an image, for example, the 256 by 256 images, we require about 24 gigabytes memory for training and lots of sampling point in the volume so that we can get a good enough result. Otherwise, we cannot get this. And one key point here is that for discriminators, we need to render the whole image for this task. But for nerve, for reconstruction tasks, for each image, we only need to render a sparse of viewpoints or sparse of pixels. That's good enough for us to do the L2 comparison and do the training task. So for again, we need more old rays, and thus, as a result, we need more memory and computation cost. And also, as you can see in the below, when we render the nerve, we always use the Monte Carlo sampling, which means some randomly sampling patterns along each ray, and which result in the details losing and bring some noise in the result shown below here. So the key challenge here is that how to achieve the high quality generation and preserve the 3D consistency in the final rendering. And to solve this, like some existing works such as the PyGAN directly use the nerve for GAN training, which keeps the 3D consistent. It's very good. But however, they cannot solve the computation and memory problems, and the result quality is very low, as shown on the left. And as shown, other methods first train a low-dimensional nerve and then upsample the rendered image with the convolutional neural networks, such as the giraffe. Although this method can generate high-resolution results, the 3D consistency, unfortunately, is lost. And we can see here the result. Later, we can also do some comparisons. You can see the result. And the key idea of our method is to define the nerve only on a sparse set of manifold surface, but not a full volume. In this way, we still use the volume rendering for image generation and avoid the view consistency issues caused by the image convolution or image upsampling here. As shown here, the sparse manifold is defined in the volume, and this sparse manifold surface greatly reduces computation and memory cost in nerve training and rendering. And also, the rendering is still the volume rendering in the object space, so it keeps or preserves view consistency here. So based on these new representations, we develop our solution as shown here. So we train a network M to obtain a distant field. So this distant field defines a sparse set of surface manifold, where the isosurface in the predefined threshold in the distant field. So the manifold, this set of surface manifold, is shared by all the nerves generated by the GAN. So the phi network is a generative network which generates a nerve defined on manifold from an input latent vector z. So given each z, we will generate a nerve for each identity. Yeah. During the rendering for each ray, we compute the intersection point between the ray and the manifold surface. You can see here. And given recasting, given each ray, we first got a lot of intersection point, their coordinate. Then we send the coordinate into the generated nerve here to access for each point. We got their density and color values. So after that, we do the volume rendering and accumulate all the colors together according to their density and transmittance, and then we got the final images. Then for the training, we use the discriminator loss here as a traditional GAN to compare, do the classification between the rendered image and the real image set. And after that, we train whole this GAN network, then we got the result. So you can see our paper later for all the details here. So here we show the image rendered from nerve generated by our method. And let me see. Let me try to do it. Let me try to got the okay. Now I can play it. You can see the results generated by our method. And also, if you look at it carefully, you can see like the hair, the parallax caused by the hair, and even the glasses you can see that the parallax is really correct. And also the image quality is very high, and it preserves all the details. And for different views, it generates really realistic result and preserves the 3D consistency. Here, if you look at the whiskers of the cat, it generates really correct parallax. And here we compare our results with the previous work. The first result you can say is a giraffe and Python. And you can see that their result preserves the 3D consistency, but render quality is really low. For the giraffe, although they can generate a high quality result for each image, however, they cannot preserve the view consistency. As shown here, you can see the cat model, cat image, and the giraffe generated here, and you can see our result. Yeah. So here we show 3D shapes extracted from the generated nerve here. Although our method is not used for the 3D reconstructions, but you can see that our nerve actually will recover or preserve the 3D details, shape details, so that the rendered image can preserve all the parallax and 3D effects here. Yeah. So here we show some quantitative evaluations as the FID scores and KID scores, and we compare our method with other methods. The traditional style GAN tool and still generates the best results because they are only targeted to the 2D image generation. So they don't have this 3D consistency and other things. For other 3D aware or used to generate the 3D representations for image rendering, such as giraffe, Python, and giraffe, and our method, you can see that generates much better results than theirs with a better FID score and KID scores. Yeah. So this work is published in the Svprd as a oral paper this year, and here we show the more results. And after this work, we also try to extend this work to further improve the image resolution generated by our method here. We call the Gram HD, and now this paper is already put in the archive. So you can say, we show the result here. Okay. It seems that the video still has some problem. Maybe I can show later. Yeah, I'm sorry. Yeah. So in conclusion, I think I just showed two research works to demonstrate that we can use the 2D image collections. It's possible to use the 2D image collections to learning the 3D representations. So I think the learning 3D representation from 2D image collections is really, for me, is really promising solutions. And the good thing is that I believe that by developing this method, we can totally solve the data problem in 3D learning. And so that, and also we can connect in the two image and video learning tasks with the 3D learning task, just because if we all of us just use the 2D image or the video data for the learning, then a lot of methods people developed for the 2D image and video learning task can be leveraged, can be used for our 3D learning tasks. And also, I'm really interested or very excited about this 3D learning by discrimination method. I think it provides a new method or paradigm for the 3D reconstructions. So traditional, you know, like in the computer vision, we have the multi-view consistency to do the 3D reconstruction. We have the shape from shading to do the 3D reconstructions. But here is a totally new setup, which means for each object instance, we only have one image. But after we have an image collection of the object in one class, it's still possible for us to do the 3D reconstruction for each object in the class. Yeah, but on the other hand, I think on one hand, we can say here is that the learning 3D representation from 2D convection is very promising. But on the other hand, I would like to say, and learning 3D representation from 2D image collections is still a very open problems. There's still a lot of challenges here. For example, how to develop other unsupervised or semi-supervised method for learning by reconstructions, where very limited 3D data, or even without 3D data, how to develop it is still unknown problems. Now people have some schemes for the material maps, as shown here, or for the face data. And for general 3D shapes, how to do this way is still unknown. And the other things is that I just mentioned that the 3D learning by discrimination is totally a new way for the 3D reconstruction. However, the theoretical foundation behind it is still unclear. For example, we want to know how many images do we need it so that we can do this 3D learning or 3D reconstruction by discriminations. And in what conditions we can do this, or in what conditions we will fail, right? And for which class we will success, definitely. And for which class or what shape representation or what shape distributions we may fail or we cannot recover that, is still unclear. And the other things is that it seems that we have two approaches. It's one called the learning by reconstruction. We use L2 reconstruction loss. One is the learning by discrimination, which means we use a discriminator or GAN loss to do this training. So the relationship between these two and how to combine them together for the learning, the 3D representation learning, is still unclear problem. It's worth us to do more investigation and explorations. And finally, I would like to thank to my colleagues and collaborators and interns for their contributions to the work and I mentioned in this presentation. And here I show this project web for the papers, data, model, and source code. And welcome to visit our web page and try the source code and try the models there. And here is my talk, and thank you for your attention. Yeah.
All right, thanks for Dr. Tong gave an impressive presentation, and we have a few time for a few questions. So I think all the audience can put your message on the online stream or like the AG webinar session in the Bilibili, or any questions? All right, so at first I have a few questions. So now the virtual reality, we represent the 3D using the VR. So by the way, now we can reconstruct our 3D contents for many different ways. For example, in real time, like the RGBD camera or dual camera or simple 2D images from 2D to 3D. So, but the qualities and also the computational resources consumption is quite different. So from the quality and the strength, so what should be the next thing will be applied in the virtual reality for the recovery step?
Oh, recover that, you mean recover the 3D content from the real world, right?
Yeah.
Yeah. I personally, let me say, I think I personally is very interested in the recent progress on the nerve or the neural radiance field. The reason is that if you look at the nerve works, and if you don't really want or how can I say ground truth 3D reconstructions or 3D shapes, for example, if you want to some manufacturing things, definitely you need the 3D reconstruction. But if you only want to put it in some virtual world, I want to show it or visualize it, I think the nerve provide really good representations for both appearance and the rough shapes there, and provide really realistic high quality result here. Of course, there are still a lot of issues such as rendering costs there, memory costs there. But I think that people are making really rapid progress to solve these problems. On the other hand, if you look at recent really great work at the news works, and based on this nerve representations, if you change it to the surface signed distance functions, you can really got how can I say, I would like to say the amazing result for 3D reconstructions. When I look at the result there, I say, oh, that's impossible if we use any existing 3D reconstruction way to do these works. So I'm really excited about it and say that will be a really great way to do the 3D reconstruction. And another way, as I mentioned here, very interesting is I call the 3D reconstruction by discrimination or 3D learning by discriminations. So this GAN framework provide another way is that if I don't have a lot of image on one object there, right? But if I have a lot of image of one object class, such as the apple, and if I have some fruits there, right? Still, by collecting this image and train generative models, I still can get a lot of 3D models and relatively 3D representations can generate a very realistic image of the different objects in the class. That provide a totally new way for me. So yeah. So I think these two approaches are really promising and may solve a lot of existing problems we face in the past decades, I think. Yeah.
Sure, that's great. Thanks for your answer.
Yeah.
So any other questions? So if we don't have any questions, so we can move to the next session.
Sure. Thanks.
Sure. All right. So
let
at
me
first, okay.
Stop the share. Yeah.
Yeah. Okay. So let me introduce our second speaker, who is Shenhuang Beik. I spent a few years to pronounce his name, and even I found from his website, he has a pronunciation record in his website to teach everybody to know his real pronunciation. It's Shenhuang Beik. So this topic is about the differentiable computational imaging with light. Shenhuang Beik is the assistant professor from the postdoc in Korea. Before he joined postdoc, he worked as a postdoctoral research associate at Princeton University and holds a PhD degree in computer science from KAIST. His research interest lies in computer graphics and computer vision with a particular focus on computational imaging and display. His work aims to capture, model, and analyze high-dimensional visual information of the real world originating from the complex interplay between the light, material appearance, and the geometry. To this end, he designed end-to-end computer imaging and display system for fundamental scientific analysis, as well as diverse application domains. So welcome, Professor Shenhuang Beik.
Thank you. Right. Thank you for nice introduction, Qilin. And can you see my screen here?
Yeah, sure.
All right. Then let me start my presentation. And thank you for inviting me as a speaker for this great opportunity. And today I would like to talk about differentiable computational imaging with light waves. So these days, we are surrounded by many imaging systems. For instance, in AR, VR glasses, the vehicles, autonomous vehicles, robots, our mobile phone, and even medical devices. And this shows the importance of well-designed imaging system for diverse applications. And conventionally, digital imaging refers to the process of recording the reflected light photons from a scene using lens. And then we record it with our electronic sensor, which gives our raw sensor measurements. Then we process it into a visually pleasing image. And we share the captured image with our friends and people. Then with the advance of computer graphics, computer vision, machine learning, and so on. Now what we do these days is to put reconstruction algorithm, or in other words, as a form of computation to process this raw data or processed image data to recover some hidden information about the scene, such as the semantic classes, depth information, material, or surface normals. And what I'm interested in here in this pipeline is, instead of putting computation only as a post-processing unit here, we're about to put the computation for all different aspects to the illumination, scene, optics, sensor, raw data, or the other parts as well. Then the goal here is to improve the accuracy of the previous reconstruction algorithm, but also go beyond that to enable complete new applications. And this field is called as computational imaging. And as a computational imaging researcher, I want to tackle the problem of capturing, modeling, analyzing, and exploiting light waves for graphics, vision, imaging, and display applications. And these days, I'm focusing on reconstructing the shape, depth information, appearance, and also I'm interested in the holographic display. Overall, these are the 8 main directions that I'm pursuing these days. And because of the time limit today, I like to introduce only 4 of these. The first one is the differentiable camera. So in order to explain what the differentiable camera is, let me give you the example of the human vision system and how that evolves to the current vision. So our human vision system consists of 2 main parts. One is the sensing part, the other is the processing part. And sensing part, of course, consists of our human eyes. And on the left side, you can see how our human eyes, its optics and its neural system has evolved to the current one. And in the process of this evolution, our human brain also cooperatively has evolved to our current form to coordinate with this input visual information to live our current life, right? So here the point is that our imaging system and hardware imaging system and the software processing unit, they have cooperatively evolved together. Now let's look at our how these imaging devices have been developed in modern days. So what we do is we create this really nice hardware system that collects the light into this sensor. Then the sensor is super high resolution, so it gives this the nice chameleon image, for example. Then we have a neural network these days to process this image and extract some hidden scene information. Here in this example, such as the class of this image that gives the estimate of this chameleon, right? Then we have a loss function, which is used to train this neural network. And this is how this current camera has been developed. But what we do find difference of this development with our human visual system is that this one only trains our processing unit, which is the neural network here, right? So what differentiable camera aims to is that we train or we optimize both our imaging system and our reconstruction method software jointly in order to do something more interesting by only without having too much trouble of looking at this given single hardware fixed system. So for instance, let me give you an example in the context of depth imaging. So depth imaging is the problem that aims to estimate the distance between a camera to a seen object, right? And its applications are quite diverse in AR, VR, robotics, or in autonomous vehicle. And these are the applications that is required to understand the geometric structure of the surrounding, right? And in order to do this, we need to have this depth imaging capability. One of the depth imaging systems that is particularly attractive is active stereo system. So you may heard about the stereo that has 2 cameras nearby capturing a scene. Here in this example, we are capturing a single bunny with two cameras. Then in active stereo system, we employ a structured illumination module that emits a specific illumination image to a scene. You can think of it as just a projector. So we have this active stereo module in Kinect or in Intel sensor and so on and so on. Then what is going to happen is that when you capture this scene with your two stereo cameras, you are not only capturing this bunny, but also capturing the projected illumination pattern on top of this object. Then the idea of active stereo system is to utilize this projected illumination pattern as a matching cue to extract the depth information. Here, one thing to note that is that this what illumination pattern is made with this active stereo system is determined by an optical element called as diffractive optical element, DOE. This DOE is a simple optical element that is made of really small the slab of glasses with different thicknesses. This glass has the size of like the micrometer pixel pitch with the thickness of also micrometer or in the order of millimeter that generates some certain phase shift for the different light waves. And how to fabricate or how to determine this the micron scale thicknesses of this glass slab, we're gonna dictate this illumination pattern of this structured illumination module. Okay, just keeping that in mind, let's move to how this active stereo systems has been designed in a conventional manner. So here, this is the 2D graph that shows the design space of the active stereo system. On the vertical axis, we have the illumination image. Here, you can interpret this the vertical design space as the potential illumination image that you can generate with the DOE. In the horizontal axis, we have the reconstruction method. So a certain dot here in this reconstruction method could be a neural network or could be a different form of reconstruction method for depth estimation. And then this the 2D graph tells you the expected depth error. What that means is that if the value is low, then that combination of a illumination image and a reconstruction algorithm will gonna give you the better depth estimation or better depth imaging capability in terms of depth. Then what people have been doing so far is that they first hand engineer the specific illumination image, right? They find some patterns that could be probably easy to be fabricated or look random as possible, something like that. They first fix the illumination image in the hardware. Then a software scientist or engineer takes it over, and given that illumination pattern, they've tried to find the best reconstruction algorithm. It could be a new neural network architecture, or it could be a more simple and efficient form of reconstruction method. Then they're gonna give you some local optimal in this design space. What we proposed in this work, in the principle of differentiable camera, is that let's try to optimize this illumination image and reconstruction algorithm jointly together to find hopefully a global optimal, or at least better local minima than the previous fixed pipeline-based method. So here is the rough pipeline. We start with a DOE phase map that we want to optimize, right? And then we try to optimize this DOE phase map and the reconstruction algorithm together to estimate the better depth. So here, the main idea is that given the given the DOE phase map, we can estimate or we can simulate what kinds of stereo images that we are going to capture in simulation, right? Then we have a reconstruction neural network that are going to estimate the depth information for given these stereo images. Then if we have the ground truth depth map in simulation, we can compute the loss function, which will gonna be backpropagated through this reconstruction network to the DOE phase map. if everything is implemented in a differentiable manner, then we can jointly optimize this DOE phase map and reconstruction. Here, important thing is that the DOE phase map, we're gonna determine what kinds of illumination pattern that we are going to use. And reconstruction algorithm is the network that we're gonna process the stereo images captured under this specific illumination pattern to estimate the scene depth, okay? We obtained the optimal illumination pattern and reconstruction algorithm in simulation and fabricated the obtained illumination, obtained the DOE profile as an imaging system shown on the right. And here are the actual the demo of our imaging system, including our fabricated learned DOE and our neural network. Here you can see that we can estimate the scene depth quite accurately for diverse the scene objects, low reflectance specs, specular stop sign, diffuse color checker, and even transparent bubble wrap. Okay, let's move to the next topic, which is the reflectance imaging. In the reflectance imaging, I like to particularly focus on the polarization, which is a wave property of light. And polarization is related to the orientation or oscillation pattern of the electric field. And as we all know, the light exists as waves, and it consists of the electric field and magnetic field oscillating with each other in a perpendicular manner. And the oscillation pattern in time of this oscillation pattern of this electric field in time is polarization. And specifically, if we draw a tangent plane with respect to the direction of this light propagation, and if we project this electric field's oscillation pattern to this plane, they're gonna give you some oscillation pattern in this 2D. And this 2D oscillation pattern is polarization, and it could be linear polarization, circular polarization, elliptical polarization, and so on and so on. And you may be not familiar with the polarization of light, mainly because we humans cannot sense the polarization of light, right? We cannot distinguish the light with a certain polarization from another polarization of light. So, however, in the nature, we have many living mechanisms that can distinguish the different polarization states of light. And here is an example, the popular mantis shrimp that can distinguish the light with different polarization states. And the reason that they have developed this capability of sensing polarization of light is because the sensing polarization could be helpful for their living, right? And people have identified also the benefits of using polarization for diverse applications. And we have made use of polarization for example, for our sunglasses, or distinguishing the reflection on the windows, or estimating the detailed shape information of an object, or the shape information of a translucent statue, which is very notorious for obtaining its shape using existing methods. We can use polarization for distinguishing the seemingly similar two different cells under this RGB examination, but can be distinguished by using the polarization, such as this the tumor cell and the normal cell. Or we can use the polarization for separating the different layers of human skin that could be used for accurate digital human projects. For enabling all of these applications, what is fundamental is the polarimetric bidirectional reflectance distribution function, or so-called polarimetric Prdf. So let me introduce what that is. Polarimetric Prdf is the concept that we're going to tell you how the light polarization is changed after reflection on a object surface for a given arbitrarily instant direction of light, and then for the arbitrarily the outgoing direction, how its polarization states is changed. The polarimetric Prdf, or PBRDF, describes that as a function. Okay, so this may give you the impression that it is similar to the BRDF, of course, because it has the name of the BRDF in it, right? And actually, the BRDF describes how intensity of light is changed upon reflection, right? For an instant the direction and for an outgoing direction. So here, interesting thing is that polarimetric BRDF is a superset of BRDF because polarimetric BRDF also describes intensity changes, not only its polarimetric change. So in our previous work, what we did is to propose an analytical model of polarimetric BRDF based on Miller-Stokes formalism, Fresnel theory, and microfacet theory. So it is too much detail if I explain these terms one by one. Here, important thing is that this is the very first analytical model that describes the diffuse and specular reflections of light in terms of its polarization. So it is a simple formula in the end. By making use of some knowledge in optics and tremendous efforts in computer graphics, especially the microfacet BRDF models. Based on that model, we built an imaging system using a camera and a DLP projector equipped with linear polarizers in front of them to reconstruct the shape and the appearance. Here, appearance means polarimetric BRDF from a fixed viewpoint. Note that conventional methods for acquiring shape and appearance typically requires capturing the object at different spatial positions and directions. However, our method enables this from a fixed viewpoint by making use of the additional information that we can gather from polarization. However, after doing this project, what we realized is that our polarimetric BRDF model is difficult to validate. Why? Why it is difficult to validate this analytical model? It is just because we don't have the ground truth data or ground truth real-world polarimetric BRDF data that we can test our analytical model on to that, right? In order to solve this problem, we conducted a follow-up work to collect this real-world polarimetric BRDFs. To this end, we built an acquisition imaging system that has illumination module on the left side, and then we have a sample made of a homogeneous material with the shape of the spherical the object at the center. On the right, we have the camera module equipped with some polarizing filters and spectral filters. Then we have these polarizing filters in front of the illumination and then camera module, which we rotate one by one and capture multiple images. At the same time, we also rotate this turntable, which will gonna change the orientation of the instant light to the sample. In this way, we can provide the whole different instant illumination angle to the some material, right? We also have spectral filter in front of the camera that are going to provide the additional information of polarization in terms of different light spectrum. We also capture everything in HDR mode. So here is the example video of our captured material. This is a gold spherical object. On different rows, we show the captured video at different light spectrum, light wavelengths. And then also in the same row, we show different videos for the different polarization filters angle. Of course, by rotating our turntable. In this way, we captured the very first polarimetric Prdf dataset that covers large directional space. Also, it describes the complete polarization change of light. It has 25 real-world materials database. Okay, and this is the very first polarimetric Prdf dataset that we can use to analyze the polarization changes under the real-world condition. What we can do with this polarimetric Prdf is to improve or analyze or simulate how polarization of light changes under some ideal condition. So here is a typical rendering of some robots in a path tracing renderer. So this is the intensity RGB rendering result, right? But now that we have these polarimetric Prdfs, what we can do further on top of this is to simulate how polarization states of light change during this light transfer, right? On the top left side, this is the degree of polarization. So more black color means that the light is unpolarized, meaning that light is randomly polarized. More reddish color means that the light is polarized to a certain direction, or it could be circularly polarized. On the top right side, this one tells you whether the light is linearly polarized or circularly polarized. On the bottom side, they show the orientations of circular and linear polarization. Not only doing this simulation, what we can further do is to find out the relationship between the various material properties with polarization. Here on the left side, we show the white billiard ball, its captured intensity and its linear polarization direction. Okay, here you can see that the linear polarization's orientation is related to the surface normal, as indicated by this color. However, what we can find out here is that in this chrome material, the linear polarization's direction does not tell you about the surface normals of this object. What we found out here additionally is for this metallic chrome material, actually circular polarization's orientation encodes some information about the surface normal on this metallic material. This new insights gives a hint that it might be possible to extract surface normals of metallic material by analyzing circular polarization. Another observation that we made is the relationship between surface roughness and polarization. On the left side, we show two samples. One is spectral one, which has very rough surface profile. On the bottom side, we have the ceramic material, which has the really specular appearance, as indicated by the specular highlight at the center. If you look at AOLP, which is the orientation of the linear polarization, or DOP, degree of polarization, you can easily see that the surface roughness, high surface roughness makes this surface normal dependency of linear polarization angle and degree of polarization weaker. Okay. Another interesting observation we made is that if we capture real gold material and fake gold materials, in the RGB domain, it is difficult to identify which one is the real one. However, if we look at the orientation of circular polarization, interestingly, their orientation of circular polarization are completely flipped with each other, which we're going to tell you what is real and what is fake material. That was the reflectance imaging part. And let me move to the time of flight imaging. Time of flight imaging aims to measure the time it took from the emittance of light from a camera and then its arrival after the travel in the scene. And these time measurements, we're going to tell you about the distance between the camera and the mirror here. In this graph, the x-axis is the time of flight and y-axis is the detected number of photons. So since the emittance of the light, we measure how long does it take from the arrival of the how long does it take the light back to the camera, right? And this time of flight information can be converted into the depth information of the scene based on this simple formula, depth equal time of flight multiplied by speed of light divided by 2. And this time of flight application can be shown in these nice visual examples of emitting the light into the entire space and measure its reflected time to recover its depth information. And as you saw, the applications of time of flight imaging are quite diverse. And it has time of flight imaging can be categorized into the two major different directions. One is the direct time of flight camera. The other is the indirect time of flight camera. And for the direct one, we have this time of flight imaging module in our mobile phone, autonomous vehicle, and also in the airborne devices. For the indirect time of flight camera, we have it on our gaming devices, AR, VR devices as well. So as you just saw, we have two different technologies in this time of flight imaging. The first one is the direct time of flight imaging, and we use the typically APD or SPAD SPAD sensors for this direct time of flight imaging. For the indirect time of flight imaging, we often use photonic mixer device called as PMD. Okay, we use the different sensing techniques for these different time of flight imaging modalities. Now, let me show you some our recent work regarding this direct time of flight imaging. As I mentioned before, time of flight imaging measures how long does it take from the emittance of light photons to the arrival of them. But in the real world, if we have the real bunny here, even though we emit the light photons at a small period of time, when they reflect back to the camera, we now suddenly have this long different kinds of like the photons with different time of flight, just because there are numerous light passes happening in the interaction of light with this light matter, with this real object. And that generates this long tail histogram of detected light photons with different time of flights. What people have been doing so far is that they collect, even though they collect all of these photons, they do care about the first arriving photons in order to estimate this in-depth information based on the previous formula, which is a valid way because the first arriving photons are likely to be related to the real depth information of the scene. However, what we wondered is that what kinds of information do we have in the first arriving photons? Do we have additional information that we can extract from those photons? And that's what we investigated. And for the first arriving photons, it is related to the direct surface reflection. And each time of flight information, we're going to tell you the depth from that object surface to the camera. And here, if you look at the polarization states of this surface reflected light, we found out that it is related to the surface roughness of that object. However, for the late arriving photons generated by the subsurface scattering inside of the surface, so here you can understand these late arriving photons as a result of light that is that penetrates the surface of the object and then interact with the molecules inside of this object, and then in the end exits from the surface and then captured by our camera. And what we found out is that the polarization state of these late arriving photons depends on the surface normals and scattering properties of this object. Based on this observation, we presented a new Prdf model that incorporates the temporal dimension on top of our previous polarimetric Prdf. So what it does is it tells you how light intensity and polarization changes in time upon reflection. We propose a Miller matrix function, 4x4 function, that is dependent on the temporal delay, instant, extant directions, and some scene parameters. Here, it is very similar to our previous polarimetric Prdf, but the difference is that we added additional dimension of light transport, which is the time of flight. This we're gonna tell you how scene parameters is related to the captured measurements of time of flight camera in consideration of polarization. Given this, our proposed temporal polarimetric Prdf model, in order to acquire those data, we built an imaging system consisting of picosecond laser that emits the light to a scene. And we have some polarization filters and galvanometer that are gonna allow us to scan through this scene. The light is reflected from a scene and then captured by a SPAD sensor, the direct time of flight sensor. We have the beam splitter and polarizing filters as well. This imaging system gives us the raw measurements of polarimetric time of flight imaging. So here, before evaluating our method on real scenes, we evaluated on some synthetic scenes. This is the synthetic, this is synthetic intensity image of a scene. Then our method enables us to extract the accurate depth information this synthetic scene. Here is the comparison to the conventional time of flight method that only utilizes these first arriving photons reflected from the object surface. Note that in contrast to this conventional time of flight, our method utilizes all photons, including first arriving and late arriving photons, and their polarization states in order to reconstruct this accurate depth information. As you can see here, our method also supports the direct estimation of surface normals and other material parameters such as refractive index, surface roughness, and some scattering properties. I'm gonna skip the details here, but what I want to tell you is that our temporal polarimetric Prdf model provides the link between these scene properties and our measurements. And by using that, we can estimate these properties inversely based on some gradient descent based method. We also, of course, evaluated our method on real objects, and we used the measurements acquired from our experimental prototype. Here is the result from conventional time of flight, its surface normals and depth information. As you can see here, conventional time of flight method couldn't resolve these geometric details in the measurements. Our all-photon polarimetric time of flight imaging were able to capture these defined detailed geometries. Okay, next, let me give you the example of how we can improve the indirect time of flight imaging based on computational imaging method. In order to do that, let me explain the correlation time of flight or indirect time of flight imaging in general. Here we have the indirect time of flight imaging camera. What it does is it basically emits some illumination to a scene similar to the direct time of flight. And there is a scene. If we zoom in here, if you look this into details, our illumination emitted from time of flight camera has interesting intensity modulation pattern in a sinusoidal way. So in other words, our time of flight camera emits intensity modulated illumination to a scene in a sinusoidal manner. Then after hitting this target scene, the intensity modulated light will be reflected back to the camera. Based on the depths between the time of flight camera and the target, there would be phase shift between the emitted light and then the detected light from a camera. And this phase shift can be used to obtain the depth information. So our goal in this indirect time of flight imaging is to obtain this phase shift to recover scene depth. In order to do that, we have a special sensor called as photonic mixer device or PMD. And inside of this PMD sensor, what it does is it has some reference signal that is aligned with the intensity modulation pattern for the illumination. And then this signal is correlated with our reference signal that are going to give you some constant value that could be decoded to estimate the scene depth. However, the problem of existing correlation time of flight imaging is that we have noise added in this photon electron conversion process. So what that is that when we have instant photon on this photonic mixer device, that photon will be converted into the electron, right? And then we process this electron in an electric manner, and we compute this correlation in the electric domain to estimate the true phase shift information. However, in that conversion process from photon to electron, there will be some inevitable noise added. What we proposed in our recent work is that we move this correlation computation procedure in the optical domain so that we don't do this photon to electron conversion for this correlation computation. In this way, what we aimed for is that we calculate this correlation, of course, almost without having some noise information added. Okay. this allows us to use conventional intensity sensor instead of the specialized PMD sensor, which will gonna even make our method practical by making use of this truly advanced sensor technologies for the intensity sensors. Then this gives us the true advantage of using the optical modulation, optical correlation, and this allows us to increase the modulation frequency of our illumination. So what that is, on the left and the right, here are the sinusoidally modulated illumination intensities with different modulation frequency. On the left, we have a low modulation frequency. On the right, we have high modulation frequency. Here, given a same depth change of a scene, we have much higher contrast on the right, right? And this means that we can distinguish two different surfaces with slight depth difference if we use this high frequency intensity modulation. And however, previously, in a previous time of flight imaging system, it was too difficult to utilize this high frequency modulation because of the inevitable noise in the photon to electron conversion that I just described. However, in our work, because we moved this correlation computation from the analog domain to the optical domain, now we are much more comfortable with handling the noise. So we can increase this modulation frequency quite a lot to achieve this high depth sensitivity. Here are the examples of using the different modulation frequencies of the illumination. When we use the 100 megahertz modulation frequency, we can potentially estimated the dragon objects would look like this. However, if we increase the modulation frequency by 10 times, resulting in 1 gigahertz modulation frequency, now suddenly we can estimate the rough geometry of this dragon. If we increase it up to 10 gigahertz, we can see the fine details of this dragon, right? And this example gives you the sense of how modulation frequency is important in terms of the depth resolution and precision. We built an imaging system that implements all of this idea that's shown on the left. And on the right, here is the scanning procedure of our imaging system. So our system also is based on the galvanometer, as shown in the previous direct time of flight system. And we are here illuminating a scene with the really fast intensity modulated light, okay, at 10 gigahertz actually. Let's say that we built our imaging system that could capture everything in that fast, the intensity modulation frequency, and that high intensity modulation frequency, then still we have some important problem to solve, which is the phase wrapping problem. So on the left, this is the simulated depth of a synthetic scene, spans from 1 meter to 1.7 meter. On the right, this is the corresponding the scene. And if we have an indirect time of flight imaging system that capture this scene with 100 megahertz modulation frequency, then what you're going to achieve, what you're going to obtain is the phase shift from 0 to 2 pi, as shown on the left. Here, you're going to notice a clear boundary on this pillow and on the sofa between the 2 pi to the 0 pi, just because there will be inevitable the phase wrapping, because phase is only defined from 0 to 2 pi, okay? And then in order to obtain the accuracy in geometry from these phase shift measurements, you need to solve a phase unwrapping problem that you're going to solve this, that you're going to convert this one into a continuous depth estimate, depth information. And in a previous imaging system that uses this 100 megahertz modulation frequency, it was relatively trivial to convert this one into a proper depth map. However, this problem gets extreme when we use high modulation frequencies. For example, when we increase the modulation frequency to 1 gigahertz, as shown on the right, now suddenly this number of phase reps in this scene jumps to the 5. When we use 7.15 gigahertz modulation frequency, which we used in our experimental prototype, the number of phase reps suddenly jumps to this 35. And unwrapping these measurements is not trivial anymore. Even more difficult, our imaging system utilized 2 different measurements at 7.15 gigahertz. The other is 14.32 gigahertz. I mean, this additional information of the second frequency definitely helps to decode this problem of the phase wrapping. However, still having these 2 measurements poses a new problem of accurate phase unwrapping. Okay. In order to handle this problem, we proposed a segmentation-inspired phase unwrapping neural network. So we're going to skip the details, but the general idea of this network is that we interpret this phase unwrapping problem as a different form of image segmentation. So we want to estimate the correct phase label as a kind of semantic label, right? For the given phase maps. So for each of the phase map region, we want to estimate its phase map index as semantic label. Okay, so that's what we did, and we utilized different kinds of the techniques developed in the recent neural network based approaches, such as the Fourier feature encoding and accurate scalar Gaussian noise modeling, and so on and so on. Let me show you the result. And here is the scene that we captured, this nice, the old man bust. And this is our raw measurements, which is the 7.15 gigahertz phase shift from 0 to 2 pi, of course. Here is the additional measurements that I mentioned at the 14.32 the gigahertz. And this is the reconstructed depth information, right? Here you can see that our phase unwrapping method were able to successfully decode this complicated the many phase wrapping problem. And to more visually examine the result, here is the point cloud, the visualization with the different illumination, the lighting direction. As you can see, our optical, the gigahertz modulation in the hardware and the software-based, segmentation-based, the phase unwrapping network helped resolving the severe noise problem and so on and so on. And we obtained this really nice reconstruction of this bust. Okay, let me now describe our the final topic, which is the multi-dimensional imaging. As you saw in this today's topic, I touched the different aspects of light transport, right? It could be the spatial light transport or temporal light transport or polarization light transport. These are the fundamental dimensionalities of light. And space, of course, means that the light could be propagated into the different direction. Time means that light has a finite speed, so we can measure its travel time. Polarization is the wave property of light related to the oscillation pattern of the electric field. And all of these different properties, we can extract the different information about the scene, right? Then a natural question arises here is that what about to utilize all of these different dimensions of light all together? So here in our last year paper, we try to do exactly do this, and we call it as polarimetric spatial temporal light transport. And we aimed to model and extract how light bounces off on the scene in terms of polarization, direction, and time. Okay, all of these three things together. First of all, there was no theory or no mathematical formulation about this high-dimensional light transport. So we proposed a tensor theory, which models the instant light with different directions, different polarization states, and different time with a single tensor P. And also similarly, we model the outgoing light as a different tensor I. And they are related here through a light transport tensor T based on tensor formulation. And this tensor formulation is very high dimensional, different from the conventional the vector matrix multiplication. In fact, this instant light has three dimensionalities. Outgoing light has 4 dimensionality, and light transport, most importantly, is modeled as 7D tensor, which is really high dimensional compared to the conventional the light transport. And capturing this 7-dimensional light transport was too difficult with the existing devices. So what we had to do is to capture a partial information of these 7-dimensional light transports with 2 different imaging systems, which are all novel by itself. On the left side, we have the spatial temporal imager that captures the spatial light transport on top of the polarization light transport. On the right-hand side, we have the coaxial temporal polarimetric imager that enables us to capture the light transport in terms of polarization and time, but not in spatial dimension. With these 2 separate imaging modalities, we demonstrated many applications that could be benefited from analyzing these different dimensionalities jointly. The first one is the shape reconstruction. As you just saw on the left side, we have the dragon that consists of the really translucent material, which complicates the reconstruction of its shape using conventional techniques. For instance, on the middle, this is the reconstruction results of its surface geometry using structured light, which is one of the D-factor, the 3D scanning method. As you can see, its results are not that good in terms of its surface normals. However, by analyzing both spatial and polarimetric light transports, our method enables accurate surface normal reconstruction as shown on the right. I'm going to skip the details, but this is only possible because we looked at the light polarization and spatial dimensions together. Also, what we tested out is the descattering. This is the clear view of a ruler and a doll right behind a glass that contains some water inside. We have our spatial polarimetric imaging system in front of this scene that consists of a camera and a light source. And we pour milk inside of this glass that are gonna limit this visibility of the scene quite significantly. This is just because some of the light emitted from our illumination module will be directly reflected from this milk particle inside of this glass, instead of penetrating all of this and then reaching to the dome and ruler and then reflected. And the relative the amount of light intensities coming from this rear door and ruler gets much smaller than before. We found out that by analyzing the spatial polarimetric light transports together, we are able to see through this dense scatter quite effectively, as you can see on the right. I'm going to show you another example, which is Birefringent Analysis. Here we have interesting crystals, and some are transparent here and here. Some are the opaque, as you can see on this here and here. If we capture this interesting crystal scene with our spatial polarimetric imaging system, then we can even examine the surface of this transparent crystal, right? As we all know, examining the surface of the transparent objects is quite difficult. However, by analyzing the polarization states of light jointly with its spatial light transport allows us to examine the surface profile of this transparent crystal, and also find out some polarization specific characteristics of real crystals that could be useful for finding out useful minerals in the geology. The last example is the metabolism detection. On the left side, we have two apples, and one is real apple, the other is fake apple. So it is difficult to distinguish them in this RGB captured image, right? However, by analyzing the spatial polarimetric characteristics of the light transport, we are able to distinguish the real apple from the fake apple, because fake apple has unique the polarimetric reflectance property different from the real one. Okay, that was it. Today I covered the 4 different topics of my recent researches. And as you saw, I study how to capture, model, analyze, and exploit light waves for graphics, vision imaging, and vision display applications. And that was it. And I'll be happy to take any questions you may have.
All right, thanks for Dick's nice presentation. So any questions? We have a few time for questions. So I have a question. So hi, Dick. There is one problem I have seen before, especially for the subscattering of time-of-flight sensing. No matter how, especially for the indirect time-of-flight. For direct time-of-flight, we can capture the histogram is okay. But especially for some material with subscattering, when we're imaging with the indirect time-of-flight, do we have any faster way to correct the depths introduced by the error of the subscattering?
Yeah, that is a great question, and I think there is no solution, unfortunately, for now. So there have been many attempts for correcting the interreflection thing in this indirect time-of-flight imaging system, but those directions have been mainly centered around correcting the large-scale interreflection, so-called multipath interference, right? However, the scattering generated inside of the surface, which is called as subsurface scattering, has received less attention in the indirect time-of-flight imaging regime, just probably because it's insufficient information to extract that, right? And however, it would be very interesting to find out some ways of doing that. Probably that should start from mathematically modeling that procedure. That could be related to my temporal polarimetric Prdf model or some other things as well. Yeah, but that could be an interesting future work for sure.
Do you think it's using the polarimetric, we can use in polarimetric time of flight to do some correction or coding to solve this problem?
Yeah, I think there might be some ways of doing that, but in order to correctly untangle this complicated polarimetric properties change by both multipath interference and subsurface scattering, I believe that we need to first simulate everything in simulation, in a renderer, in a synthetic renderer, and see some patterns or hints about the relationship between this multipath interference, subsurface scattering, and time of flight polarization.
All right, that's great. So Dr. Tuxin have one question. Let me repeat his question. So for the first work, I think currently your method is designed for offline usage to determine the light patterns. Is it possible to adjust the pattern to associate the hardware in real time during the capturing?
Yeah, that is a great question. And that's actually our ongoing work as a future direction. So yeah, that is definitely possible. And we are pushing ourselves towards that goal to enable real scene adaptive the 3D accurate imaging.
Cool.
Yeah, thank you for great questions.
Thanks. Thanks. Yeah.
So do we have any other questions? All right, no more questions. So thanks for Dr. Tuxin and the Professor Xinhuang back again. And also thanks for all the audience and also the AsiaGraphics committee. So today we have already extended for 10 minutes. So we can stop over here. And thanks for everybody again.
Thanks. Thanks, Professor. Yeah, hi. Thanks.
Goodbye.
Yeah, thanks all the audience. Bye-bye.
Bye.